So we have completed this chapter, right? So we'll do some problems based on these chapters which are important. Then we'll move on to the next one tomorrow. Okay, second chapter will start it tomorrow. So what are they completed in your school? They started this chapter.
They started dielectrics.
Dielectrics, okay. Okay, we are ahead then. Okay, shall we do some problems then? So those who are online are able to hear me?
Yes.
Yes, sir.
Now can you confirm? Those who are online, can you confirm again? Are you able to hear me?
So it's actually echoing. So both the mics are.
So one minute, I'm not able to hear you. Wait. Now speak.
So it's echoing right now.
Am I audible now? Is it better now?
Yes, sir.
Okay. So we'll start with some problems. So before that, are there any doubts from any topics? So you approached me with some problems, right? I will do them. We'll do them today. So I'm only going to give you the outline calculation part. I'm expecting you to do it. Is that clear? Right. So we'll start with this number. So if I take example 1.6, okay. So let's say there are three charges of magnitude Q1, Q2, and Q3, each equal to Q. Okay. At the vertices of an equilateral triangle of side L, what is the force exerted on the fourth charge capital Q placed at the centroid of the triangle? Answer. We have already done this problem. Please. Answer is 0. Right. So you guys know how to do it, right? So one is draw the force due to each individual charge, then resolve it into components and solve. If you see the horizontal components, they will get cancelled out and the vertical components will get cancelled. Hence, the net force is 0. You can check your notes for clarification. Similarly, let's do example 1.7. Consider three charges Q, Q, and minus Q placed at the vertices of an equilateral triangle. What is the force on each charge? So if you see the question, here the question is about what is the force on each charge? Meaning, how many charges are there? Three charges. So each charge will experience the force due to the remaining two charges, right? So if it has to happen, then if this is Q, and this is minus Q, right? That is what they mentioned. So how will the force due to the charge at point 3 be due to the remaining two charges? So if I take this as the first charge, second charge, and third charge, the force experienced by the charge at point number, okay, we'll start with 1 itself. The force experienced by the charge at 1, what is going to happen? So due to the negative charge, there is an attraction, and due to the next positive charge, there is a repulsion, right? What is going to be the magnitude in both the cases? Because magnitude of all the charges are same, and at the same time, the distances are also same, except, right? When that is the case, if I take this force to be F, this force to be F, if I draw a free body diagram of point A, I know that this force is F and this force is also F. And how much is this angle? Okay, that is 60. Then this angle is going to be 120. So what is going to be the resultant? FR will be equal to root of F square plus F square plus F square plus F square plus 2F square cos 60 or 120. Cos 120, because you need to include the angles between both the forces. So how much is it going to be? Minus half. Cos 120 is minus half. So this will be root of F square plus F square minus F square. So 2F squares will get cancelled and you're left out with F. So the resultant force experienced by the charge at point A due to the remaining two charges in the system is the force itself. So clear? Please make a note of it. I hope everybody understood, because I didn't write the mathematical values. Is everyone convinced with the fact that both the forces F12 and F13 are same? Yes. Because it's an equilateral triangle. Right? This force is F, this is 60. This is 60 means how much is this angle? 120, linear pair. No? That's the reason. Done? See, what about the force experienced by the charge at B due to the charge at A and C? Let's think of this fact. Okay. Let me take a separate page. A, B, and C. Correct? So what is the charge at point A? Q. Charge at point B, Q. Charge at point C, minus Q. Okay. Now what is going to be the direction of force experienced by the charge at point B? Due to whom? Due to A, it is away from it. if I call this force, how should I name it as? If I say this is 1, 2, and 3, this I'll call it as F21. Then what about this force? Right? Force experienced by the second charge due to the third charge, right? So what is the magnitude of this? It is kq square divided by the distance square. Then what about the magnitude of this? This is also kq square divided by L square. If you observe, I didn't take the minus into consideration. Why? Because vector. For vector, if I know the direction, I'll not take the minus sign into consideration. Then the angle between these two, 120. So the resultant will be root of f square plus 2f square cos. So again, the answer is going to be f only. This is simple. Then what about the charge which is present at point C? So due to this positive charge, the force is in this direction. Due to the charge at point B, the force is in this direction. So this force is F, this force is F. What is the angle between both? Resultant, root of f square plus 2f square cos 60. How much will it be? So it will be root 3f. If you want, you can calculate and see it will be root 3f. Is that clear to everyone? So this is a good problem. Done. Right. We'll move on to the next part. Now see. There is, so mark it as important. There is an electron that falls through a distance of 1.5 centimeter. So page number 21. There is an electron that falls through a distance of 1.5 centimeter in a uniform electric field. So what do you mean by uniform is? Set of parallel lines, right? So uniform electric field of magnitude, how much value? 2 into 10 power 4 Newton per Coulomb. The direction of the field is reversed, keeping its magnitude unchanged, and a proton falls through the same distance. Compute the time of fall in each case and construct the situation with that of a free fall under gravity. So are you able to understand what they're asking? So what is that? Instead of gravitational field, you have electric field. And in that electric field, in the first scenario, what is happening? There is an electron drop. Look at the way electron is dropped. So electron is dropped from a point closer to the negative charge. So what will happen to it? It will experience repulsion, right? Now comes an important question. Repulsion is a force. So when the object is experiencing force, it is going to accelerate, right? So what is the amount of acceleration experienced by it? If I say this distance is h, okay, then what is h equal to? H is equal to ut plus half at square. But it is released from rest, if I'm not wrong. Right? So u is 0. Then h will be, h is the distance between both the plates, is equal to half into acceleration is how much? So it is f upon m into t square, or half into, what is the value of force experienced by this charged particle? It is q multiplied with e. So do you know this formula? So you know that E is equal to F by Q, then F is equal to Q into E. So QE divided by M into T square. Right? Here, what is the charge, guys? Half into E into capital E. What is small e? That is charge of each electron into capital E divided by m into t square. Correct? Right. Now, having said this, what is going to be each value? If you substitute each value, you will be able to calculate the time. So, how to calculate the time? So, T will be equal to root of 2h into m divided by small e into capital E. Correct? So, when you take the scenario of electron, this is the value. So, please make a note of it. If there is any doubt, get it clarified. I am assuming that everyone is clear. Small t is time. Small e is charge of electron. Capital E is the electric field. Because force is what? Force is Q into E. This force that I wrote here is the electrostatic force. Electrostatic force is equal to Q into E. That is what I wrote. Instead of Q, I replaced it with E. Is that clear? Now, how to do the next one? Will you guys try it? So, in the same electric field, if you take, see, the direction of electric field is reversed. Right? In that scenario, you're dropping a proton. Now, what will happen? So, the same thing is what you're going to get. If I call this as T dash, that is root of 2h into mass of proton divided by the charge of proton into electric field. But the charge of proton and electron are the same. Which one is heavier? So proton is heavier. So who will take more amount of time to reach the negative, reach the opposite end? It is a proton that is going to take more amount of time. Is it clear? Yeah. Now they are asking us to compare this with that of a free fall. How will you do that? Okay. So what will you write? H will be equal to half into, in the place of acceleration, you will write gt square. There is a acceleration due to gravity. So T will be equal to root of 2h divided by. So there the mass is not going to play an important role. Hence, this will be the difference. Right? Right? So with this, we'll go to the next problem. That is, there are 2 point charges Q1 and Q2, each of magnitude plus 10 into minus power 8, 10 power minus 8 coulomb and minus 10 power minus 8 coulomb respectively are placed 0.1 meter apart. Calculate the electric field at point A, B, and C. You want to try this? Okay, first, don't copy. See, generally in exam, right, this is not the kind of diagram they'll give you. You need to convert the given statement into a diagram. So what did they give us? They gave 2 point charges. First, place those 2 point charges. So 1 point charge, put a plus sign and a circle around it. They need to give diagram because ABC is required. But I can give you a statement also for that. Okay. You should be in a position to draw it. So first, take a positive charge and negative charge. Both are of magnitude. How much value, guys? 10 power minus 8. And how much is the distance of separation between them? 0.1 meter. Right? Now, calculate the electric fields at point A. So instead of point A, they can say calculate it at the midpoint of line joining both these charges. So what is point A? That's what, right? So it is the point, the midpoint of the line joining both the charges. What about point B? Point B is at a distance of 0.05 meter on the left of positive charge. They need not say left of positive charge. If this is the question, they will say it is at a distance of 0.05 meter from charge, from the positive charge along the line joining both the charges. Are you able to understand what is right? Similarly, what about point C? Point C is perpendicular to the line joining these two charges, and the distance from the midpoint is how much? They could have given something, right? So this distance they would have given it. If that is the case, will you be able to draw the diagram or not? That is what I'm trying to ask, right? Now I have an important question to be asked. Both are of equal magnitudes and they are separated by a certain distance. Can I call it as a dipole? Why? Because the distance is slightly higher. You can call it as a dipole only when the distance is in terms of your nanometer or angstrom. Here it is in terms of 0.1 meter. So it is point B. I cannot call it as axial point and directly apply the formula of Kp divided by R cube. No, sorry, 2 Kp divided by R cube. I can't apply it. Similarly, C is not the equatorial point. You cannot apply Kp divided by R cube. So what are you supposed to do? You have to go step by step and then solve this problem. So shall we start? Right. So if I take point A, due to the positive charge, what is the direction of electric field at point A? Sorry, due to the positive charge, what is the direction of electric field at point A? Away. It is along the line joining, but away. I'll call this as EA. This is A. Oh, sorry. I'll call this as E1. And what about this? I'll call this as E. Correct? Now, these two electric fields are the same in magnitude, but they are same in terms of direction as well. So what is going to be the net field at point A? It is going to be 2 times E, right? So 2 into, what is the value of E, guys? K into Q is 10 power minus 8 divided by 0.5 square, accepted. So 0.05 square. 0.05 square, accepted. But the value of K is how much? 9 into 10 to the power 9. Okay. Now this is the meaning. Okay, this is in terms of magnitude. What about the direction? EA vector will be equal to 2 into this value times I cap. Correct? So please copy this. In a similar manner, try what is going to be the electric field at point B and tell me. Is there anyone who is not able to understand? Those who are online are able to understand.
Yes, sir.
Okay. Calculate the point B, guys. Huh? So you have to go. Just a minute. Yeah.
So the direction. For the positive charge, it's away from it, and the electric charge is towards it. So we should subtract.
Okay. Okay. So if you take the positive charge, the electric field at this point is away from it, and if you take the negative charge, the electric field. So electric field due to this. If I take this as 1 and 2, this is E1. This is E2. Accept it. So the net electric field will be equal to E1 vector plus E2 vector. Okay, Mike. See, when you're writing principle or superposition, you should write it as plus only. After that, you will take minus sign. So E1 minus E2 in terms of magnitude. Okay. The result of this in terms of I cap. So now you will be able to calculate it. So how much will you get? Calculation part, you do it. As I mentioned at the beginning of the class, calculation, I'm leaving it to you. I'm only teaching you the concept. If there is any doubt, you can reach out to me later. So what about point C? So due to the positive charge, the electric field at point C is away from it, and due to the negative charge, it is towards. So this is E. This is also E. The resultant of these two will be how much? The angular basis. So how much is cos theta? This is theta. This is theta. It is not 60 because they didn't mention it's an equilateral triangle. It is a, oh, sorry, it is an equilateral. Sorry, I didn't look at it. It is an equilateral triangle. So this is going to be 60 and this is going to be 60. So obviously, this is equals. Right? You can resolve them into components and solve, or you can take it as root of E square plus 2 times E square cos of 120 degrees. So wherever cos 120 degree comes, the first E square and this one will get cancelled. Okay. So then you can solve it. Answer will be E only. If you are able to know the value of electric field due to a single charge, you'll be able to find the value. I hope it's clear, right? Anyone with a doubt? Clear? Shall I move on to the next one? Yeah. Solve this. So two charges plus 10 microcoulomb are okay, plus and minus 10 microcoulomb are placed 5 millimeter apart. Determine the electric field at point P on the axis of the dipole 15 centimeters away from the center pole. Since they themselves mentioned it as a dipole, you can use a formula. So what is the formula? On the axis, axis means 2 kp divided by r cube. Seriya? So 2 into k is 9 into 10 power 9. What about P? P is how much? 10 into 5. Yeah, it is 10 into 5. This is 10 power minus 6 into 10 power minus 3. The whole divided by r cube. R is 15. So 15 into 10 power minus 2, the whole cube. If you solve this, you will get the answer. Which one? It is not 10 mm, it is 5 mm. But they mentioned it, no, so we need not worry about it. They themselves will call it. No. In the previous problem, they didn't use the word dipole. Okay. Now, what about this case? At a point Q, which is 15 centimeter away from point O on a line passing through O and normal to the actual, use Kp divided by Rq. Okay, use Kp divided by Rq. That will give you the answer. Okay. Right. So, where, 10 into 5 up. See, what is the dipole moment? It is the magnitude of product of either of the charges and distance of separation between them. So either of the charges has magnitude of 10 microcoulomb. So 10 into 10 power minus 6 into 5 millimeter. So the distance between the charges is 5. Yeah. Next. So this problem we completed, right? 1 minute. 1.11 we have done. This is done, right? And what about this problem 1.12? This also we have completed. Last class I think we did it, right? This is another problem that we will try to solve. So it's slightly tough. Let's read the question carefully. So an early model for an atom considered it to have a positively charged point nucleus of charge Zt surrounded by uniform density of negative charge up to radius capital R. Okay, this is one of the models of atoms which was proposed earlier. Okay, this is the scenario. The atom as a whole is considered to be nucleus, is considered to be neutral. For this model, what will be the electric field at a distance smaller from the nucleus? Where they have taken smaller in two different places. Huh? One is at point P and the other is inside. You're able to see there is a small r, this one. This distance you're able to see. No? So they are asking what is the value of electric field at those points. So how do we even proceed first? Okay, you can consider a Gaussian surface, right? Where will you consider? Inside, right? Inside and outside. Okay. So first I can consider a point r less than capital R. So when I say small r is less than capital R, where is it considered? It is considered inside. Now comes an important question, right? So what is the charge of the nucleus? Given, what is the charge? And I'm not asking about the nature, magnitude. They've given it in the question. If you read it carefully, positively charged point nucleus of charge Zt. And they told atom as a whole is neutral. So all the negative charges put together is going to have how much charge? Minus Z. Yeah, Zt of magnitude, right? But if I take this distance r alone, and if I consider a Gaussian surface here, right? If I do something like this, will that part consider the total charge of electrons present in it? So what is enclosed within it? It is only the charge of the nucleus plus some amount of negative charge from that of electrons, accepted. Right? Now, we need to find that some charge due to the electron that is contributed in that small radius r. Is that clear? Now, what we are going to do is this kind of a problem, you can solve it using Gauss law because it follows symmetry. It's a simple thing. You need not use Coulomb's law here. Since it's an extended object. So what does Gauss law tell us? The total flux that is coming out of a given or a closed surface is equal to 1 by epsilon naught times the total charge that is enclosed by that surface. Correct? So I have drawn a surface with that red color dot you're able to see. So first job that we are going to do here is find out what is the total charge present in that nucleus. Sorry, present in that small sphere. How do I do that? So how do I do that? We will calculate flux and then we'll calculate. Sir, any other worker? So I'm only concerned about, I'm not even concerned about flux now. I'm only concerned about how to find the charge that is there in that small portion. Ratio of what? Okay. So, okay. So I gave you certain steps to solve Gauss law, right? In that, what was the first step that I told you? First is identify the type of charge distribution that is present. So what is the type of charge distribution present here? So the charge is distributed over volume or area. This is where we make mistake. It is volume because it's a solid sphere. Whereas when I discussed about spherical shell, what did I say? Since inside it is hollow, wherever mass is not there, the charge will also not be present. That is why the charge went and resided on the surface. Whereas in this case, the charge is distributed over the volume itself. And it is uniformly distributed, if I'm not wrong. So they gave uniform density. So uniform means if you take a particular volume, the ratio is always a constant. So rho is equal to how much gas? So what is the density of this nucleus? Can I write it as minus ZE divided by 4 by 3 pi capital R cube? That is going to be the density because I'm ignoring the size of the nucleus. Right? Consider to have positively charged point nucleus surrounded by uniform charge density. So now we need to calculate what is the electric field at that point. So for electric field, I'm saying flux is equal to, listen to this carefully, flux is equal to the charge enclosed by the Gaussian surface divided by epsilon naught. Right? So flux is how much? The line, the loop integral of E vector dot dA vector is equal to the charge enclosed within whom? Within that smaller surface divided by epsilon naught. So the line integral of E into dA into cos 0 degrees is equal to charge enclosed divided by epsilon naught. I hope it is clear to this step. So I'll take that E outside. E into the surface integral of dA is equal to what is the charge enclosed in that smaller portion is. This is where the trickiest part is. So how do you calculate the total charge that is present? So ZE plus how much? So listen to this. If I take the density of the nucleus to be rho, then rho is equal to minus ZE divided by 4 by 3 pi R cube. What is the meaning of this? Try to understand. This much amount of charge minus ZE is distributed over a volume of 4 by 3 pi R cube. Then what will be the density of this particular portion? So it will be ZE plus, or I can say ZE minus Q divided by 4 by 3 pi small r cube. You're able to understand? Right? Where ZE minus Q is going to give us Q enclosed. Because I'm taking that smaller portion, right? Within that smaller portion, what is present? You have the nuclear charge plus the small amount of negative charge. So Q enclosed, how can I write it as? Q enclosed will be equal to small rho, that is rho into 4 by 3 pi small r cube. So, but what is rho? Minus ZE divided by 4 by 3 pi capital R cube into 4 by 3 pi small r cube. 4 by 3 pi, 4 by 3 pi will get cancelled. So E into the surface will be equal to minus ZE divided by R cube into small r cube. Where? Because I ignored the size of the nucleus. Where? I didn't say that I calculated the density of nucleus. I calculated the density of charge that is present in the bigger region. That is the density of the negative charge. Okay. So when this is the case, E into what is line loop integral of dA? 4 pi small r square, that is the surface area of the sphere, is equal to minus ZD divided by R cube into small r. So this and this will get cancelled. So E will be equal to minus ZD divided by 4 pi R cube into small r. Okay. So what did he do? Did I miss epsilon naught? I wrote only charge divided by epsilon naught is there. So ZD divided by 4 pi epsilon naught. Where, no? Which, the one which I did? Which? This one, huh? Are you asking about this one or this step? This one, left hand side, this step. What happened? I took the charge from here and put it. Oh, it is R cube. Sorry. I thought it is R and wrote it. R cube, sorry, R square. This is R cube. Sorry, it was my mistake. I thought it is R. Now it is R cube. No, this will go. So minus ZD into R divided by epsilon naught R cube. So how much is the value? E is equal to minus ZD divided by 4 pi epsilon naught small r divided by capital R. This is going to be. Charge includes, I added both these values, the ZD and that small amount of charge. ZD minus Q means, see, the nucleus is there, no, it has a charge of ZD. And this portion is there, no, it has a small amount of negative charge. So this one and this one, if you follow the additive nature of charges, is it not ZD minus Q? So that ZD minus Q is what I called it as the total charge enclosed. So that's how we wrote that. Okay. So how did they do? Because I took charge of this one only into consideration, negative charge. Because they didn't give us the size of the nucleus. No, I must generally. No, here it is. This is not mass density. No, this is charge density. Which one should be 0? Okay, then it should be root 0. Then how will you take it into consideration? How will you take the density of the charge into consideration? Okay. 1 minute, wait. I'll take a separate page and solve. See, read the question carefully. Consider to have a positively charged nucleus of charge ZD. Okay, where is the charge ZD? This positive charge is Z into E. Accepted? Okay. Now, what are they saying? It is surrounded by uniform density of negative charge up to radius capital R. So this capital radius R is a place where the whole of the negative charge is concentrated, accepted. Now, what is the type of charge density you can define for this kind of a scenario is what my question is. What is the type of charge density you can define? Huh? That's what I did. So what is that volume charge density? Volume. Okay, what did they do? The charge distribution for this model of an atom is shown. The total negative charge in the uniform spherical shell, uniform spherical charge distribution of radius capital R must be minus ZD, accepted. Why is this minus ZD? Because the atom as a whole is neutral. So I'm saying the sum of all the negative charges put together is minus ZD. That's what they also gave. Since the atom has nucleus of charge ZD plus the negative charge, it is neutral. So this immediately gives us the negative charge density. So we must have, what are they trying to say? 4 by 3 pi capital R cube into rho is equal to how much? Why did they take 0 there? Which one is the same 0 there? What is the explanation they gave? We consider two situations, R is less than R is capital. Okay, when R is less than R, this phi is equal to E of R into 4 pi R square, accepted. Okay, this is what we did. So net charge enclosed by the Gaussian surface is equal to the positive nuclear charge and the negative charge within the sphere of radius small r. Okay. So this is the step I wrote. If you guys understood what I wrote, 4 by 3 pi small r cube into rho. Rho, what is it defined as? That is ZT divided by. I'm repeating it again. I'm saying minus ZT is distributed over the larger space. So why am I not taking the nuclear charge into consideration? It occupies, but what will you write the volume? What is the volume you are going to write? That's what you're saying. The nucleus is small, where you're saying maximum charge is distributed only throughout the sphere for this kind of a model of atom. This is only for this kind of model. It is not for the whole atom. Okay, that is what the question specifically says. It is something looking like Thomson's model of atom, right? It is similar to that, but it is not the case. So in this case, if you have to write density, okay, whatever type of charge density you are asked to write, you need a denominator. Right, in the denominator, which one is occupying the maximum volume? Is the negative charge occupying the maximum volume or the positive charge? That's what my question is. Convinced? So what I'm trying to say, that is the reason why it is minus ZD. See, the value of magnitude of charge is same. So what exactly you are going to learn here is, inside the nucleus, you can ask me, sir, there is a charge of plus ZD, but this much size is occupying minus ZD. The problem here is the nucleus is highly packed. Okay, it is going to be very much compact, and you call it. So that's why it becomes unstable in certain cases where there is an unbalance. Okay, if the number of protons or neutrons are changing. That's what you learn in nuclei. So with respect to this question, I'm trying to write the charge density stating that this atom consists of maximum occupancy of negative charge. So that is why I wrote a minus sign divided by 4 by 3 pi capital R cube. Is this step clear or not? This is the first step you need to understand. Because if I write plus ZD, what is the volume I am supposed to write in the denominator? R, you don't even know what is the size of the nucleus. It's generally R naught, which is 10 power minus 15. 10 power minus 15 of the cube incubed. Okay, that is the reason why you ignore it. That is the reason why they wrote it as 0. Okay. So when it is ignored, this is going to be the density. Are you clear with this point? So when this is going to be the density, what is the total amount of charge enclosed by the Gaussian surface? By the surface that we have considered in small r radius, what is going to be the charge? Now you need to take the nuclear charge into consideration. I'm not saying nuclear range or volume is taken into consideration. Nuclear charge is still not an ignorable value, but when it comes to density, it is ignorable. Okay, so the total charge enclosed, can I write it as the charge within the nucleus, that is Ze, plus how much will be the part of the negative charge that is present? Density of that particular negative charge multiplied with 4 by 3 pi small r cube. 4 by 3. Is there anyone having doubt in this? 4 by 3 pi small r cube. But what is the value of rho? This one. Ze divided by 4 by 3 pi capital R cube into you have 4 by 3 pi small r cube. So 4 by 3, this and this will get cancelled. So you will write Ze minus Ze into R cube divided by capital R cube. So this is Q enclosed. In the previous case, what I did, in the step itself, I took this charge as Q enclosed and did the manipulation. Now I'm doing according to textbook. Okay. So this, when they have taken this as the scenario, I hope you understood all these things. E into the loop integral of dA is equal to charge enclosed is Ze minus Ze into small r cube divided by capital R cube. Right. So what is this value? The surface integral of all the values taken on the Gaussian surface is how much? 4 pi small r square. So E into 4 pi small r square is equal to Ze minus Ze divided by capital R cube into small r cube. Now take the r square to the other side. Oh, sorry. I'm forgetting that. So upon epsilon. Now when you take it to the other side, you will get the required answer. Now when the value of small r is greater than capital R, what will happen? When the value of small r is greater than capital R, then what is going to be the net charge enclosed by it? It will be 0 in this. Because atom as a whole is neutral. Oh, that's what you meant by saying. Okay. The electric field will be 0. So what is the meaning of electric field being 0 in this scenario is the number of electric field lines leaving the surface is equal to the number of electric field lines entering the surface. Okay, this is a very, very important point. Make a note of it. Don't worry, I've not seen this question being asked in boards. Okay, but it's for your knowledge. Second part, yes, they might ask you. Second part is simple only. I hope you understood that when you take a Gaussian surface outside with small r being outside as the radius, if you consider a surface like this, then the total charge enclosed in this case will be equal to 0. Is that clear? So when it is 0, electric field will also be 0. Is there anyone having that? Is the concept clear? You need to practice it to understand. That's a different story. Now we'll do some more problems which are slightly easy. Let's do it faster. I am coming. So we'll do from 15th till 20th. Okay, start with 15th. So consider a uniform electric field E whose value is 3 into 10 power 3 I cap Newton per Coulomb. What is the flux of this field through the square of 10 centimeter on a side whose plane is parallel to the YZ plane? So what is the direction of aerial vector, guys? I've already told this to you. So direction of aerial vector is always considered perpendicular to the surface and in the outward direction. Whereas with respect to a two-dimensional surface, you are free to choose. Generally, with respect to a two-dimensional surface, always choose it along the direction of electric field to make things simpler. Okay, so electric field in this case is 3 into 10 power 3 I cap. So it is in the direction of positive x-axis. Right. And where is the square placed? The square is placed in the YZ plane. So in the YZ plane means, then how is the aerial vector for that surface? X-axis. So it is along the positive x-axis itself, I can say. So what is happening in this scenario is electric field and aerial vector, they are in the same direction. So what is going to happen to the electric flux, guys? So electric flux will be equal to E vector dot A vector. So wherever they have given you the electric field and aerial vector in terms of orthogonal unit vectors always follow the dot product of multiplication. If the angles are given, go with EA cos theta. So, yeah. So E vector dot A vector, E vector 3 into 10 power 3 I cap dot, what is A vector? That is 10 into or 10 into 10 power minus 2 the whole square, the same I cap. So what is happening here? It will be 3 into 10 power 3 into 10 power minus 2 into I cap dot I cap is 1. So this will be equal to 3 into 10 power 3, sorry, 10 power 1, that is 30 Newton meter square per coulomb. So the total flux that is coming out of this surface is going to be 30 Newton meter square per coulomb. So that is the first part of the question. What about the second part? If there is anyone who's not clear, please get it clarified.
Sir, I have written 10 to the power minus 2 the whole square.
Yeah. So
Okay,
this
so
is 10 power minus 1 the whole square.
Okay, sir.
Understood?
Yes, sir.
So 3 into 10 power 1, that is going to be 30 Newton meter square per second. Now do the second part. What is the flux through the same square? Same square in the sense its dimensions are not changed. The same square, if the normal to its plane is making an angle of 60 degrees with the x-axis. So 60 degrees. Sorry, no?
You should multiply by half, sir.
Perfect. So this is electric field and the area is tilted in such a way that the aerial vector is making an angle 60 degrees with x-axis. 60 degree with x-axis the same as 60 degrees with the electric field itself. Okay. So what will happen in this scenario? Flux will be equal to E into A into cos 60. E into A is how much? In the previous problem we got it. So E into A is 30. What is cos 60? Half. So it becomes exactly half of previous value, Newton meter square per coulomb. So it is 15 Newton meter square per coulomb. Is there anyone who's having a doubt? Here, you are able to visualize the diagram? So this is an important point. Okay. We'll do one last problem. Right, we'll try that. So look at the 16th question. Sorry. Is it fine if can I erase it? So if you look at the 16th question, right? What are they trying to tell us? What is the net flux of the uniform electric field in exercise 1.15? That is the previous problem. So electric field is still the same. How much is it? 3 into 10 power 3 I cap, right? Through a cube of side 20 centimeters, oriented, so its faces are parallel to the coordinate planes. What is the meaning of this? So if I take a cube, then if I take a cube, see, I just took random things. Electric field is in this direction. So first phase and second phase will have the aerial vectors parallel and anti-parallel to the electric field. So for first surface, the aerial vector is this side, and for the second surface, the aerial vector is this side. Accepted. Now, what is going to be the flux through the remaining four sides? Zero. So flux through the remaining four sides is 0 means the total flux is going to be contributed only by phi1 and phi2. So what is the value of phi1? E into A into cos 180 degrees plus flux through the second surface is E into A into cos of 0 degrees. Accepted. So E into A, electric field is constant, aerial vector is constant in both the cases. So cos 180 is -1 and this is +1. What will be the answer? So the net electric flux through this kind of a cube is 0. Okay. Right. So we can try few more problems tomorrow in the first 10 to 15 minutes. Then we'll go to the second chapter. Clear? So I hope the concepts in this chapter are clear, right? So revise it and come. If you have any doubts, let me know. Okay. 18th. 18th, you need to complete a cube. Okay. That's right. What is the answer given? In second. What is the given? That is what I want. So what is the total charge? 10 microcoulomb, no? So what is 8.85 divided by 6? That's so if you have no doubts, 1.47. 1.47, right? It's ready. If you are ready to do, I'll give you. It is because of the aerial vector. So this is the direction of electric field. Here also the direction of electric field is this side. Aerial vector is to the right for this surface. Aerial vector is to the left for the first surface. So when you do the dot product, then what you can say is the number of electric field lines leaving this surface is exactly equal to the number of electric field lines leaving this surface. It will always be 0 provided the electric field's direction is not different. Because we did the same kind of a problem here. You remember this one? So those who have no doubts and not a part of math class, we can leave. So if you take this problem, for example, electric field is in this direction. Electric field is in the opposite direction. In this case, aerial vector is to the right. In this case, the aerial vector is to the left. But in this case, what will happen is the net electric flux through the flat surfaces will get added. Whereas in this, in the problem, previous problem, cube problem, what has happened is, it is because electric field is also supporting the aerial vector. Whereas in the previous problem which we did, electric field is opposing aerial vector in one case, supporting in another.
15th question, we had the electric field in a particular direction and the area.
This one, 15, this one, huh?
So it was the previous one.
Okay.
We had the area in the area vector in 60 degrees to the electric field.
Okay.
Electric flux means the number of electric field lines that are passing perpendicular to the area. Right?
Yes.
So in this case, the electric fields in this direction. So how did we get a non-zero value for the amount of electric field lines that are perpendicular to it?
Perpendicular to the surface are parallel to aerial vectors. Huh? Think about it.
Yes, sir. That would mean the electric fields in the horizontal direction.
Electric field is in horizontal direction. Aerial vector is also in horizontal
So
direction.
it was in 60 degrees to the electric fields.
This is electric field.
Yes, sir.
This is the aerial vector.
Yes.
So this is 60 degrees. Only few components of electric field were passing through this 60 degrees. That is the meaning. So that is why it became half. Correct.
But if you calculate the answer is not matching.
Those who are online, if you have no doubts, you can find them.
Sir,
Yeah.
Sir, what about the test, sir, which you told? Will we have it this weekend?
No, not this weekend. This weekend is a long weekend. Most of them are not there. We'll have it next weekend.
Okay, sir.
Okay.